is on organic light emitting devices fabricated by screen printing process. As you all know, in general, organic light emitting device, which is called OLED, can be divided by two different kinds, which are small molecule OLED and polymer OLED. The fabrication technique for small molecule OLED is typically by using vacuum sublimation. And for polymer OLED, people use inkjet printing, usually. In order to make organic light emitting devices easier and cheaper, it is useful to use mass production process such as printing, conventional. For organic light emitting diode, we are dealing with organic materials which is wet processable. It is possible to use printing process. So in my talk, I would like to focus on conventional printing process such as screen printing and gravure printing or offset printing. I'll introduce organic light emitting device and printing techniques of organic thin films and screen printing process for organic thin films. And also I explain experimentals and results and conclusions. Next, please. Okay. As you all know, organic light emitting device, which is called OLED, has three different layers. One is a transparent electrode with high work function, such as ITO. And another electrode is cathode with low work function, such as calcium or lithium fluoride aluminum. In between them, we have organic hole or electron transport material or emitting organic layers. The benefits of OLED is simple and low cost processing, and it is thin and lightweight, and it can be made by flexible display. The objective of my talk is, simply speaking, organic light emitting device by printing process. I especially interested in single layer OLED with low molecular weight fluorescence dyes. And for printing process, I interested in screen printing and gravure printing. The benefit of using printing process is simple and low cost, and it can extend to roll-to-roll process in the future. There is many printed OLED study what's going on abroad. There is one company named VTT in Finland. They research on spin-coated or gravure-printed polymer dyes, and they use ITO film printed on the glass, and also they use metal cathode using screen printing. And this is the picture, the device they made. And another group is University of Arizona. They use spin coating of small molecule dyes, and also they work on polymer dyes. And in Japan, there is a company named Dai Nippon Printing. They are using gravure printing polymer OLED. There is many kinds of conventional printing. I listed 4 different kinds here. One is flexographic printing. Ink is put on some area elevated on the printing die, and this printing pad is transferred to a substrate, and then ink is transferred to the substrate. This is called the flexographic printing. And another type is gravure printing. This is there is a groove in a printing pad, and ink is filled in the groove, and the substrate, the ink is transferred to the substrate by the adhesion force. And screen printing is we use mask and screen at the same time, and then we print the ink on the whole mask, and ink is transferred to the open area of the mask to the substrate. And the last kind of printing is digital printing, in which there is inkjet printing and electrophotography. Inkjet printing is the way we are using all the time, and electrophotography is the printing ink where we want ink to be printed. Screen printing process can be shown schematically right here. And there is a flexible screen which is made by stainless steel wires. This is looks like a fabric made of stainless steel wires. And we put on ink on the screen, and we pull the squeeze on it, and then pull down, and then ink squeeze into the openings of the screen, and then the films go on the substrate. The mesh number is defined by the number of threads per inch. For example, we have 40 mesh screen. That means to have 40 threads per inch, so that the opening of should be about 44 micron if the thread diameter is 20 micron. So we have about 40 microns on the opening. The chemicals we've been using is for matrix polymer, we use polystyrene and polycarbonate. And fluorescence dye, we use ALQ3 and NPB as a whole transport material. And for solvent, we use chloroform and dichloromethane. And cathode metal is lithium fluoride aluminum. And we treated ITO using oxygen plasma. The process to make organic light emitting device is the following. We clean first, and then we pattern the ITO and plasma treat the surface, and then we screen print the organic film on it, and then we deposit the cathode metal on top of it, and we finally make the device. This is the listed experimental data. I can explain. If we have PS 1.5, that means 1.5 gram polymer of polystyrene dissolved in 15 milliliter solvent. And this is mesh size. We use 3 different kinds of meshes. And we used 3 different mask thickness, and this is the final thickness of organic films after depositing, after screen printing. And we also changed it polymer amount of polymer dissolved in the metric, dissolved in the solvent, and yes. This is one example of experimental results after screen printing. If we use 400 mesh and 1.8 gram of polystyrene dissolved in 50 milliliter chloroform, we have 460 nanometer thick organic polymer film. The surface is roughness is about 4 nanometer, and the bump here is occurred when we scratch this step. If we change polystyrene to polycarbonate, we have thinner film, because we have the polycarbonate has lower molecular weight polymer here. And also, if we use polycarbonate, we have a lower roughness here, just 1 nanometer. And the surface morphology is pretty good. And we change it, mesh size, mesh count is 325, and we have the thickness of 28, and roughness is about 1 nanometer. If you change polycarbonate, we have the thinner thickness of 165 and almost the same roughness. If we change mesh count to 500 means we have very many threads in the same distance, so the opening is very small. So if we have same viscous ink, then the film thickness should be very thin. But as a result, we cannot tell what is the thickness of the film, because as you can see here on the surface, there is some patterns on it. These patterns come from the patterns of screen. So you can tell how thick the film is at this condition. If you use 500 mesh using polycarbonate, you cannot tell also the thickness. If you increase the viscosity of polymer, viscosity of ink, you can get on film surface just look like a screen mask. This is just a screen mask shape. In summary, if you increase the polymer content of the ink, and you get higher thickness organic films. In order to make organic light emitting device, you have to use organic film of thickness around 100 to 150. So you have to stick on condition right here. And the surface morphology is pretty good. This is the fluorescence microscope photography. As you can see here, this is the organic film doped with ARQ dye. If you turn on the UV light, then the ARQ3 emit. As you can see here, some place brighter and some place darker. So it's not uniformly dispersed. This is the same picture on the patterned ITO. If you use polycarbonate, which is lower viscosity, so the edge area you can define edge pretty much. If you mixing for longer time, then the dispersion of dye is pretty good. You can see there is no bad dispersion here. But this is the ink, ALQ ink. If you mix short time and mix for longer time, there is no color change. But this is the NPB ink. For NPB ink, if you mix for long time, then it's color change. I don't know why it happens right now, but it happens. This is the typical results of light emitting device, and this is the picture of OLED. As you can see before, there is not a good dispersion on dye on the sample, because that's why the light emission is come from area by area, it's scattered emission. So we tried to some different way to make multi-layer OLED. One is MPB evaporation on top of ITO and spring-plated film, and then ALQ3 evaporation film. And then in this case, you also have scattered emission. And I tried to different device, and this is the different device, but always we have scattered emission. But at last, the device, which is made by screen-printed whole transport material on top of ITO, and then evaporation of ALQ3, then you will have uniform emission from the device. This is the device which has been reported by Dr. Yabo at University of Arizona a few years ago. So this is the only way to have uniform emission from the device so far. The reason, in order to find out the reason why we have scattered emission from the film, we try to find morphology on the film. If we screen print the organic film with dye on top of bare glass and bare ITO, there is big holes on the surface. And if you plasma treat the surface, and then you will get no pinholes on top of it. And it's the same thing if you use the P-dot coated surface. If you optimize the screen printing process, you still have pinholes on the surface when you use bare glass or bare ITO. But if you treat the surface with oxygen plasma, you don't have pinholes. But you still also have brighter side and darker side. So dispersion is not that good. If you use polycarbonate, it's almost the same behavior. The surface roughness is all, in every case, is under 1 nanometer. This is the photography showing device degradation with time. If you make the OLED using bare ITO, as time goes on, the device degrades at point by point. But after a certain time, you don't get any difference because current leak through the pinholes, so there is no damages on organic films. But if you make OLED using plasma treated ITO, then there is no pinholes. So if you drive current, operate the device, then organic films getting degraded as time goes on. So the killed surface getting bigger and bigger. And it's the same thing for screen printed film on P-dot coated ITO. We finally compare the screen printing with spin coating film. As I mentioned before, screen printed film after plasma treatment, there is no pinholes and surface roughness is under 1 nanometer. But still, we have bright side and dark side. But if you spin coat the film using same ink, then you don't have any bad dispersion. It's uniform dispersion. If you take a picture of degradation behavior, if as you can see here, spin-coated device has it's degraded, but it's very uniformly. That's why the conclusion is this: using a single-layer screen-printed OLED, you only have the scattered emission from the device. But if you use single-layer spin-coated OLED, you can have uniform emission from them. So I can conclude some conclusions, which are single-layer low molecular weight dye screen-printed OLED is possible, and for a matrix polymer, lower molecular weight polymer is better. And uniform dispersion of solid is crucial for uniform electroluminescence, and optimization of screen printing conditions should be achieved for uniform luminescence solid. I think that I did not make uniform emission from the single layer screen printed OLED, but I think personally that this approach will be possible and useful in the near future. Thank you for your attention.